All right. Hi, everyone. We're on our last few chapters, and of course, our last few tests, statistical tests. I'll go ahead and share my screen. A little bit of a delay on my computer. There we go. All right. Hopefully, you can see that. Okay. So, chapter 14 we will be covering correlation and regression. So, you should have the skills to know what sum of squares are, and I have confidence that every single one of you know what that is. We have beat that over the head many times through many chapters throughout the semester. Also, you should recall what z-scores are, as well as hypothesis testing and analysis of variance. That's a little newer. That probably will require a little more practice. The rest of it, I think you probably have it down pretty well. All right, so when we're talking about correlation measures, we're talking about the type and strength of relationship that two variables have with each other. All right, so the what it describes is a few things. It will describe the direction of the relationship, whether it's positive or a negative relationship, and it will indicate what that relationship is by having a plus or, well, it will have a negative sign if it's negative. Sometimes it will have a positive sign, and sometimes it just won't have anything at all, and it's just understood that it's a positive relationship. Also, it tells us how strong or what the magnitude of the relationship is that exists between the two variables that you are comparing. So it varies on a scale from 0 to 1, 0 being no relationship at all, and 1 being a perfect relationship. And also it evaluates the form of the relationship, and most often it looks at the linear relationship. And we'll cover some of that, all of that here. All right, so here we can see a chart that is showing a correlational relationship if you plot it out on a chart like the one on the right. And the comparisons here are family income in thousands of dollars. So this actually means 3,100 and in students' average grade. So you can see, 72, they earned a C all the way to the bottom, where 95, they earned an A. All right. And so they're making a comparison between these two variables and they're plotting it out. And so if I wanted to see which one of these points on the chart belonged to person A, I would find on the x-axis their family income, which is 31. So it's likely right about above 31. And then the grade of 72, which falls on the y-axis where it shows the student's average grade. And so that would point right to this very first point on the chart. So that's how you read those. All right, so and oftentimes, let me go back for a moment. When you are looking at comparisons or correlational data, it's extremely helpful to plot it out like that so you can see the shape of the distribution or the shape of the scores as they relate to each other, because that gives us some very useful information. And one of them is whether it is a positive or a negative relationship. And you can see if you see scores plotted out, you draw a line right down the very center where the groupings are forming. You can get an idea of what the relationship is between the two variables. The first example is representing a positive relationship, which means that as time spent studying increases, so does the performance in class. So more studying means how well they did in class, which makes sense, right? The other two comparisons, performance in class and smartphone use, is showing us a negative relationship. So in this example, it's showing that the more individuals used their smartphones, the their performance in class decreased. Okay. So that's a negative relationship. So when we're talking about a positive relationship, we're talking about two variables that are both increasing. They're both going in the same direction, actually, because they could both be, um, both variables are increasing. And when we're talking about a negative relationship, we're talking about uh, both variables going in different directions. One is increasing and the other is decreasing. Okay. All right. So as far as the strength of the relationship, we can also tell what that is based on what the plot looks like after we've plotted their scores in comparison to each other. And if we have a perfect negative or positive correlation, it will look like this graph here. Well, actually, this is a representation of a negative relationship. Uh, if this graph showed scores going the other direction, it would be a positive relationship. But the point here is you can see how all of the scores are perfectly lined up. That's what a perfect negative correlation or positive, if it was going in the other direction, relationship would look like. There's one caveat here. There's in research, we never find perfectly correlated scores. You'll never see scores that are plus or minus 1. You can get fairly close, but you'll never see them at plus or minus 1. All right, so if I'm looking at this chart compared to chart B, you can see how the scores are just sort of splatted all over the place. There doesn't seem to be any shape, rhyme, or reason to these. And this is representative of what it would look like if you had no relationship. And then your score would be a 0, right? For C, this is what it would look like if you are showing a strong positive relationship. And you can see it's going up. So that is representative of a plus 0.9. If it was going the other direction, it would be a negative 0.9. All right, and here you can see in chart D, the scores are sort of hanging with each other, but not too well. And so that would be like a weak correlation. And you would probably assign a negative 0.4 to that because you can sort of see that there might be a direction occurring here. It's very difficult to tell. So it's a weak relationship. They're too spread apart. All right, so the Pearson's correlation measures the degree and the direction of the relationship between two variables, like we mentioned. Um, and with a perfect linear, and it has a perfect linear relationship. So you can say that every change in X has a corresponding change in Y if you have a perfect linear relationship. Um, and um, and this would be known as covariation. So it's covariation is a measure of the relationship between two random variables and to what extent they change together. So a perfect linear relationship is a plus or minus 1. And to calculate the Pearson's correlation coefficient, we would divide the degree to which X and Y vary together by the degree to which X and Y vary separately. So in the numerator, it's the covariability of X and Y. In the denominator, it's the variability of X and Y separately. All right. So there are other I guess, shapes you might find when you're doing evaluations. And sometimes you might see this U shape, but that would represent a no linear correlation, right? And you can see some actual outputs here. This looks more like what you might see in real outputs or real results when you do a correlation test. So you can see up here, Although these are not perfect relationships, you can see how pretty closely they are, right? Here is a positive relationship. Here's a negative relationship. You'll notice for the R that they didn't put a plus sign, but we know though that it's a positive relationship. Here you can see the plus sign, hopefully. It's kind of small. Um, and here are some weaker relationships, medium to weak relationships. The last two in this last column here are examples of no relationship, right? And the closer, even though you don't have a perfect zero here in this no linear correlation relationship, it's very, very close to a zero. Okay. All right, so before you start calculations, it is useful to put your data into a scatter plot, and you can kind of make a preliminary visual estimate based on what you're seeing. And here we have plotted the data that exists between our two variables. And you can see that our first variable is referred to as x. And since we have a second variable that we're comparing, we're calling it Y. And in correlations, we don't have independent and dependent variables. We're not, because for correlation data, it's not possible to make any claims of cause and effect. We're just looking at relationships. And something about these two variables may be related to each other, but we don't know what the cause is. That's kind of how we would interpret a correlation. All right, so this scatter plot appears to have a good but not perfect positive correlation. There's not very many scores here to really make a solid judgment on that, but you can see a relationship starting to occur here. However, for this, you might expect to see a 0.8 or a 0.9 because it is going in a positive direction. And to find the Pearson correlation, we need the sum of products, sum of squares, as well for the x and for the y variables. So we're going to look at how we calculate those for this test. So the Pearson correlation uses a ratio comparing the covariability of the x and y numerator, SP, with the variability of x and y separately in the denominator. And you can see the formula here. All right, so first we find the sum of products of deviations. It's similar to the sum of squared deviations. Okay, so we have a new vocabulary word here. It's the sum of products of deviations. The sum of products measures the amount of covariability of the x and y variables. So what is this telling us here? We take all of the scores and we subtract the mean from them for the x variable as designated by the little x here. And then we do the same for the y variable, and then we multiply them and then sum them all up. The last step, sum them all up. Hence, the multiplication step in this process is why we call it the sum of products, right? Products refers to multiplication. So it's the sum of products of deviations. And yes, we are calculating deviations. The average amount each score deviates from the mean for each of our variables, x and y. All right. We can also calculate a computational formula for correlations. And if you wanted to do that, you would follow this computational formula. But as you know, I prefer doing the definitional formula because it helps us to see that why we're calling it the sum of products, because it's the sum of the two differences scores and then multiplied, right? All right, so to find the Pearson correlation, we need the sum of products And then we need the sum of squares for x and y. So how do we do that? Well, you can see here, they're subtracting the means, which is 6 and 4, from each of the scores for x and y. And then they're squaring them. Remember, because if we added them up here, they would amount to 0. So we need to square the deviation scores. And we arrive at 64 for x and 16 for y. And then the last step is to multiply these two columns here. And here you can see uh, how we arrived at that. So let's see. Then once you have your formulas, you can plug them into your formula. Remember, here's the formula. So we find that S&P or SP amounts to, once you follow the steps, it amounts to 28. And then you plug these squared deviation scores into the bottom portion here, 64 and 16, multiply, find the square root, and we end up with 28 over 32. And dividing that, we come to 0.875. So remember, when we were looking at the plot, we estimated that the outcome would be between 8 and 9 based on what we could see on the plot. And yes, we actually got a score that's almost 0.9. All right, so I will place this Pearson's R correlation video as an extra, or some supplemental videos, so you can help, which will help you practice if you wanted to learn how to do the computational formula. All right, so Pearson's correlation and z-scores. So the Pearson's correlation formula can be expressed as a relationship of z-scores, by the way. For a sample, we can see that this is the calculation, and for a population, this would be the calculation. The difference here is n-1 for sample. All right, so z-scores identify the exact location of each individual score within a distribution, if you recall. The Pearson correlation measures the relationship between an individual's location in the X distribution and his or her location on the Y distribution. So when you have a positive correlation, individuals who score high on X also tend to score high on Y. The flip side of that is if you have a negative correlation, it means that individuals with high X scores tend to have low X scores. So remember, you have, for a positive correlation, both scores are going in the same direction. They're both rising. When you have a negative correlation, scores are going in different directions. One's going high, one's going low. All right, so let's do our first learning check. Say you have a scatter plot and that shows a set of data points that fit very close or very loosely around a line that slopes down to the right. Which of the following values would be closest to the correlation for these data? All right, answer for that one, negative 0.35, right? That description describes a negative relationship. And since the points are loosely around a line, that means it's a weak correlation. Weaker correlations are closer to 0. So it would not be 0.75. That would be a strong relationship. It would be negative 0.35. Next learning check. Oh, ooh. How did I do that? Let's see, where did I go? Okay. All right. Is it true that a set of n equals 10 pairs of x and y scores has sum of scores for x equals sum of scores for y equals sum of scores for x times y equals 20? For this set of score, the sum of products equals negative 20. Do that in your head. See if you can do it. Think of the formula. All right, for the other one, is it true that if the y variable decreases when the x variable decreases, their correlation is negative? Ooh, that's a good question. All right. So, um, for the top one, it was true. Once you plug in all those numbers that they give you to the formula for sum of products, we do find that it's a negative 20. The other one was false. Now, if you recall, I was sort of hinting at it, even though we talked about as two scores increase, it's a positive relationship. Really, it means that I did say that when two variables are going in the same direction, it's a positive relationship. So if they're both going down, they're both going in the same direction. So the the definition of a positive correlation is that both of your variables are going in the same direction. They're either both going up or they're both going down. Okay. Oops. Okay. All right. Using and interpreting the Pearson correlation. So correlations have a number of different applications. We can use them for prediction. You can use one of the variables to make predictions about the other variable. They can be used for validity. So you can measure what you intend to measure to determine whether it is a strong relationship and whether it's a good measure to use. Also for reliability, we can use it to find stable and consistent measurements. So say I want to use a survey that others have used. And I can look at their scores to see if how strong the relationships are between their scores to see if they have a strong relationship and that I would get similar results if I used that test too. Okay. Also, the closer the correlation coefficient to plus or minus one, the higher the relative validity and reliability. So that plus and minus one, which of course was a perfect relationship, the closer we get to it, it measures both things, validity and reliability. However, a high correlation does not necessarily imply high absolute reliability or validity. There's always some, you should always have room for some error, just like any other test. Theory verification, it can be used for that as well. You can test a theory by determining the correlation between two variables. Correlation describes a relationship between two variables, but like I mentioned before, it does not demonstrate causation. Very important to remember. To establish that there is a cause and effect relationship between two variables, you must conduct an experiment and follow research methodologies that require an experiment. And remember, that means you are manipulating an independent variable, you're comparing two groups, you're doing random selection, you're controlling for extraneous variables in order for it to qualify as an experimental type of research. All right. This is hypothetical data showing the relationship between the numbers of churches and the number of serious crimes. And this is an example of how and why you cannot use correlation to show a cause and effect relationship. Here, notice that this scatter plot shows a strong positive correlation between churches and crimes. And so it's positive, like as one is going up, so is the other one. So that means the more churches there were, the more serious crime there seemed to be. And these are actually taken from real data. So it is reasonable that small towns would have less crime and fewer churches, and that the large cities would have large values for both variables. Does this relationship mean that churches cause crime? Does it mean that crime causes churches? Although a strong correlation exists between churches and crime, the real cause of the relationship is really the size of the population. Right? All right, here we go. Correlation coefficient value size will be affected by the range of scores in the data. So whenever scores do not represent the full range of possible values, caution should be used in interpreting the correlation. So this is another reason why it's important to sort of develop a scatter plot first to plot out the data and look at the shape of it and see what's going on. Sometimes you can get false positive results because of the way the data is falling on your scatter plot. Here we're showing an example with a restricted range of scores, and they don't, it just means scores might not generalize to the population. The green ellipse results when the full range of X and Y values are used and there's a strong positive relationship. However, the values in the brown circle occurs when the X values have a restricted range of scores and the correlation is near zero. All right. And so this might occur, say, if you are doing a research study and you are limiting some kind of variable. For example, maybe I want to test liking for ice cream. And I decide that I'm only going to test people that are elderly, maybe 65 and older. And I exclude all the other age groups in my data set. Well, we know that children logically, or based on my experience anyway, children seem to really love sugar, and even younger people. And I've noticed that the older people in my life, although they do appreciate sugar, they don't necessarily seem to like it as much as children do, right? And so I will be missing out on that whole age group of scores. So I would only pick up some, you know, I might end up with scores that look like the chart here, where you have only a bunch of lower scores, maybe for liking of ice cream, compared to some other scores that would fill in the gaps here if I had all of the age groups represented in my data. All right. Also, if you have outliers in your data, you can end up with false positives or data that appear to have a relationship but don't. Here is an example of an outlier individual with an X and or Y values, or well, outliers are individuals with X and or Y values that are substantially different from other data in the sample. And it would be characterized by a much larger or smaller score than all the others in your sample. So it would look like the one here in chart B, for example. And it will be obvious when you plot out your scores. And this can impact the results of your study. So if this outlier is not present in my study, well, as you can see, the R for this, when you calculate it, you are given a 0.85, which can lead you to believe that you have a strong relationship between these two variables. But if I remove the outlier, I will find that the relationship is actually zero. There is no relationship at all. Negative 0.08 is almost zero. All right. All right, here we have a scatter plot of a population of X and Y values with a near zero correlation. However, if I had a really small sample size and I only selected maybe 3 people to test on my X and Y values, like maybe here, here, and here, I may end up with results that would look positive after calculating for R. Because if you are only plotting these 3 scores, it would appear that you had a positive relationship with them. But if you selected a larger sample and collected all their data, you might find that actually there's no relationship at all here. So small sample sizes can also lead to false positives. I hope you're noticing that There's lots of opportunity at arriving at false positive results when you're doing correlation scores. And so it can be very important to make sure you plot out your data so you can visualize it and make sure it's looking correct. You don't have outliers, you don't have missing data, as in, uh, restricted range data, and so on. Okay. Because a correlation coefficient measures the degree of a linear relationship between two variables on a scale from 0 to 1, it is easy to mistakenly interpret this decimal number as a percent or proportion, but it isn't. And by the way, linear means line, all right? So that's what we're looking at. But a correlation is not a proportion. Remember when we were doing ANOVAs, we were saying that we were discussing how outcomes can, or the effect sizes can be interpreted as the percentage of variability a variable has on the dependent variable. Here, that is not so. Squared correlations may be interpreted as a proportion. So once you've calculated for R, you first need to square it to show what the actual percentage of the proportion is. And the squared correlation would be called the coefficient of determination. All right, so the coefficient of determination, like I mentioned, measures the proportion of variability in one variable that can be determined from the relationship with the other variable. We can refer to that as shared variability. For example, a correlation of R equals 0.8 means that R squared is 0.64, or 64% of the variability in the Y scores can be predicted from the relationship with X scores. All right. All right. So the hypothesis test with the Pearson correlation, how do we do that? What does that look like? When we're stating the hypothesis, we actually look at the population correlation as represented by the Greek letter rho, and it looks like this little lowercase p right here. All right, so that's actually pronounced rho. So if you have a null hypothesis, which means it's non-directional, right? It's a zero. It looks like those scatter plots that are just all the scores are spread out and just splatted on there. You would say HO is rho equals 0. All right. If you have a directional relationship, positive or negative, you would say um, HO is where rho is less than or equal to 0, or H1 is rho is greater than 0. All right. Pardon me, not HO. I misspoke and I mistyped. There should be a 1. There you go. All right. So if you have a directional, it's where rho is less than or equal to 0. And if you have the other one is H1 is equal to rho being greater than 0. Right? Okay. Oh, did it again here. My goodness. Okay. Sorry about that. All right, so here we go. Hypothesis tests. Here's a sample correlation R used to test population rho. All right, the degrees of freedom for correlations is n minus 2. So the hypothesis test can be computed using either a t statistic or an f statistic. In this chapter, in your chapter, we're only showing how to do the t statistic. So we would use the t-table to find the critical value with the degrees of freedom of n minus 1. All right, and you can see what this formula looks like. And to interpret that, it's saying that the sample statistic minus the population parameter. And so remember, just like with our ANOVA test, the population parameter equals 0. All right, so we can say it's R over standard error. And you can see the calculations for standard error. So how do we do this? Here we have a researcher that is using a regular two-tailed test with an alpha of 0.05 to determine whether a non-zero correlation exists in the population. He or she has a sample of n equals 30 individuals that they obtained and produced a correlation of R equals 0.35. The null hypothesis states that there is no correlation in the population. All right, so we have degrees of n minus 2. So all of its participants were 30. So that minus 2 is 28. The critical values, when you look them up on the t-test using degrees of freedom of 28, is plus or minus 2.048. So we want to see if we have significant results here. All right. And then they calculated the R squared, which we learn from the problem that R equaled 0.35. So to square that, you end up with 0.1225. And then rho equal 0 here. And you can see how they calculated here and that the rho equals 0. So that cancels itself out and you can place it here. And then remember, our formula for error is down here, and it's 1 minus r squared divided by n minus 2. So 1 minus r squared, that's the square of r, which we find is 0.1225 divided by 28. And we find the square root of that, divide again, and we find that we have 1.98. And remember, you can draw the distribution if you need to sort of solidify for yourself whether that outcome falls within the tails of this critical value of plus or minus 2.048. And in this case, it does not. It falls in between those two figures. So we do not have a significant relationship. All right, and I will also place this video for how to do the hypothesis test for correlations as an additional video so you can practice in this week's module. All right, so we need to also, if you recall, report our results using APA format. And just like our other tests, we state if it was statistically significant. We give you the statistical value, and in this case, it's Pearson's R, the sample size, the p-value, and the type of test, whether it was a one or two-tailed test. So we would write something like preferences for femininity in male and female faces were positively correlated, where R equals 0.65, N equals 30, and P was less than 0.01. I believe this is an example from another example. So we use a correlation matrix when we report several variables, and it would look like this. So oftentimes you're making correlations with more than just two variables. So you would have to calculate for every possible 2-by-2 relationship. And when you report them, you would create a table that looks just like this, okay? And you can see the, well, here we have income and education. That looks like a pretty strong relationship. It's 0.65. It's the relationship out of all of these that's closest to 1, right? Here we have 0.11. That's a very weak-looking relationship. It's probably not significant. I'll tell you that this graph here is a lot like what you will see when you do it in SPSS, because they will often flag significant results with asterisks after them. If it's highly significant or a significant result that is less than 0.01, they'll put 2 asterisks. If it's less than 0.05, they'll put 1 asterisk. And so you can see here, we have these two, 0.41 and 0.38, are less than 0.05. This one is less than 0.01. The other 3 were not flagged, so they were not strong enough to be significant. The relationship wasn't strong enough. All right. There's alternatives to the Pearson correlation. The Pearson correlation was developed for having for data that has linear relationships that look like a line. Um, so using data consisting of numerical scores from interval or ratio types of measure scales are the ones that you would make comparisons for. So if you are comparing things like height and age or weight, time, you could use a correlation coefficient. So all numerical types of scores can be um, uh, evaluated using a correlation coefficient. Other correlations have been developed for data that is non-linear and also data that have nominal or ordinal measurement scales. There's the Spearman correlation, there's the phi coefficient, and the Point-Biserl correlation. So if we're looking, oopsie, let's go back. All right, so if we're looking at the Spearman correlation, the Spearman-Ars correlation formula is used with data that has ordinal scales or ranks. Remember, it's data that is not really numerical, but it does have an order to it, right? And it's used to measure the relationship between X and Y when both variables are measured on ordinal scales. It may be used if the measurement scale is interval or ratio when the relationship is consistently directional, but may not be linear. All right. So although in this graph here, this relationship is not linear, there's a consistent positive relationship you can see by the line. So where you have an increase in performance, you tend to see an increase in practice for this example. All right, scatter plots showing scores and ranks. You can use scatter plots to show the scores and the ranks. For the first graph, you can see that there's a consistent positive relationship between X and Y scores, but it's not really a linear relationship like you see on the right here. So you can use a Spearman correlation to do this, to evaluate this kind of data. And when you use the Spearman correlation, it will assign ranks to the data and it will sort of transform the data and help to produce a perfect linear relationship as you can see in the graph. All right, so when you have tied scores, two or more identical scores in your data, and you need ranks for Spearman correlation, there's a method for assigning ranks. So basically, when you are doing a Spearman correlation, you're assigning ranks to the non-numerical type of data, like where does it fall in the order of things. But if you have two scores that are identical, there is a way to sort of provide for that. So first you would list the scores in order from smallest to largest. Then you can assign a rank to each position in the ordered list. When two or more scores are tied, you compute the mean of their ranked position, and then you assign this mean value as the final rank for both of those scores. All right, here's the formula for the Spearman correlation. The ranks for the scores are just integers, 1, 2, 3, 4, 5. Remember, you're assigning numbers to non-numerical data, just data that has an order to it. Calculations can be simplified. You use D as the difference between the X rank and the Y rank scores for each individual to compute the R statistic. Okay. All right. And so for more in-depth understanding of how to compute the Spearman correlation, look for the additional videos that I'll include with this module on how to do that. All right, as far as the Point-Biserl correlation, this helps to measure effect size with R squared. It's a special version of the Pearson correlation, and it will measure relationships between two variables. And this is where one variable has only two values. So you might have you will have categories, and these would be called dichotomous or binomial variables. Bi meaning two, or di also meaning two. So for example, maybe you have a a sample that has college graduates versus non-college graduates. So one variable has regular, and the other variable, aside from this categorical type of variable, the other variable will have numerical scores. So maybe height, or maybe you're testing their test scores, uh, like SAT scores for college graduates versus non-college graduates. It's kind of like a t-test, or at least it uses the same kind of data. The t-test is comparing two groups on some numerical value, right, on their scores. So you would have, like, in a t-test, the example they're giving here is graduate, non-graduate, but you could also do a t-test using the same data. All right, the point Bisral R squared has the same value as the R squared computed from the t statistic. The effect size for independent measures t-test, like I mentioned before in chapter 10, can be measured by R squared. So the t statistic tests the significance of the mean difference between the two populations represented by the samples. So graduates versus non-graduates. The R statistic correlation measures the strength of the relationship between the two variables. All right. So pay attention to what the difference is here. We're looking at significant differences versus how much they are related to each other. All right. So a dichotomous variable is first converted to numerical values by assigning a value of 0 to one category and a value of 1 to the other category. So remember, we're still on this point Bisral calculation and how you compute it. Then the regular Pearson correlation formula is used with the converted data. So hence here. You should recognize this formula from the one we showed in the beginning of the chapter. R square quantifies the effect size and is entirely determined by the size of the correlation. So you just squared the results of this. And then T is influenced by the size of the correlation and the size of the sample. So the values for T and R are directly related. In fact, either can be calculated from the other by the equations, where degrees of freedom is the degrees of freedom for the T statistic. All right. Pretty interesting. So like I mentioned, both tests are very, very similar. All right, here we're going to discuss the phi coefficient test. And remember, we're looking at ways to compute a correlation when you don't have two variables that have continuous data. We're looking at computing correlations when you have two variables that either have, two variables that are categorical, or one is categorical and one is not, and so on. So, and the other one was when we were looking at the types of variables that have ranked data, right, or ordinal data. All right, here we have both variables are converted to, oh wait, did I mention? Both variables X and Y in this test are dichotomous, right? So they both have two categories. Remember, DI stands for 2. All right, so both variables would be calculated with values of 0 and 1. The regular Pearson formula is used with the converted scores to calculate R. Then the R squared coefficient of determination measures effect size. Although the phi coefficient can be used to assess the relationship between two dichotomous variables, a more common statistical procedure is to use the chi-square statistic, which we'll go over in our next chapter. All right, but these are some other options to use. Most researchers don't use this test. They will use the chi-square. It gives a little more information. However, this can be useful because it can help to tell you how much or how strong a relationship is using effect size where the chi-square doesn't do that. All right, so learning check 3. Participants were classified as morning people or evening people, and then measured on a 50-point conscientiousness scale. Which correlation should be used to measure the relationship? Can you remember what kinds of data each of these use? And which one would apply in this example? You have to think about what two variables are using and what kind of variable is it? Is it continuous? Is it categorical? Are they a mix? One's categorical, one's continuous. Knowing that should tell you which test you can use to measure the relationship here. And it would be the point-Bizarro correlation, because one of the variables has a group of 2, morning people and evening people, and then the other variable is a continuous data. It's on a 5-point scale, which suggests it's a continuous scale. All right, is it true the Spearman correlation is used with dichotomous data? Is it true that in a non-directional significance test of a correlation, the null hypothesis states that the population correlation is 0? All right, the first one is false. Remember, the Spearman correlation uses ordinal data, ranked data. Dichotomous means 2. Remember, DI means 2. Ranked ordinal data can have more than 2. And there's an order to it. Also, the second one was true. The null hypothesis assumes there's no relationship. So rho equals 0. All right. Here we're going to look at linear equations and regression. Regression sort of takes correlation to a new level, right? We're still looking at linear relationships here between 2 variables for this type of statistical test. Here you can see a line that's drawn through right smack down the middle of this data plot. And the line through the data in the graph makes the linear relationship easier to see or visualize. And it shows the central tendency of the relationship. So it's almost like defining the mean between all of these plotted scores. And it can be used for prediction. So say I know if I can calculate the formula that's related, the regression formula that's related to this particular set of data, I can use it to later predict scores. Maybe I have a score, someone's SAT scores in the future, but I don't know what their grade is or might be in the future if they were to be entered into my graduate program. I'm given their SAT scores. They're asking to come to my school, and I know their grade point average from their previous school and their SAT scores. So I can use this, their SAT scores to predict what their grade point average would be in the future. So that's the difference here, where correlation sort of helps us find how strong a relationship is between 2 variables. Now we're using a little more complicated analysis to be able to predict scores. All right. And so we call also, not only is this line a measure of central tendency, we call this the line of best fit. All right. So because it's the line that fits right down the center of the data. All right. All right, so here we have SAT scores and college GPA for engineering students. The line in the graph defines a precise one-to-one relationship between each X value, which are the SAT scores, and a corresponding Y value, GPA scores. All right, so a linear relationship between 2 variables, X and Y, can be expressed by the linear equation X equals BX plus A. You might remember this maybe from high school or lower level classes as x equals mx plus b. Same thing. So x and y are the steady variables, just like with correlations. In regression, though, x is referred to as the predictor variable or the independent variable. Here we have some new vocabulary. And the y is referred to as the criterion or dependent variable. We don't call them the independent and dependent variable because here again, we still cannot assign cause and effect between the two variables. We can only say that if someone, for example, has SAT scores of a certain number, they're more likely to have a future grade point average of a certain number. It does not say necessarily that the SAT scores are the cause of their future grade point average, right? We just know the two are related. All right, so we're seeing in this regression equation where the x and y are placed so that we can make calculations. So to expand further on this formula, a and b are fixed constants. The value of b is called the slope. Remember you learned about rise, run when you were doing graphing? Hopefully you remember in lower level math classes calculating for slope. So the slope determines how much the y variable changes when x is increased by 1 point. All right. So A is where the line crosses the x-axis. All right. So right there. So we have the y-axis and the x-axis. Pardon me. I meant to say crosses the y-axis. A is where the line crosses the y-axis, which is here, not the x-axis. I think I said x-axis. All right, here we have an example. A gym charges $35 membership fee and $15 per month. The relationship is described by a linear equation. So we have $15 a month. We would plug it into the formula here, and with an initial membership fee of 35. So remember, A is a fixed constant, and where the line crosses the Y line, so you would place that here. And then the B is the slope, the amount of increase or decrease for each unit increase in X. So Y is the total cost criterion, and we can consider that the dependent variable right here, and or the y-axis, yes. And then the x-axis is the number of the months or predictor, which is the independent variable. All right, so did I mean, let's see. Okay, pardon me. So regression is a method of finding an equation describing the best fitting straight line for a set of data. Remember that. And so we want to know how we define, or well, the way we define the best fitting straight line is when there is many possible straight lines. The answer, a line that is the best fit for the actual data, is one that minimizes the prediction errors. So prediction errors are how far away from the line any one score falls away, right? So this straight line is one that when it's placed, it reduces the amount of prediction error, right? It's right. In layman's terms, you would say it is the line that is drawn directly in the middle of all this data that is plotted out here, okay? So regression mathematically defines the distance between the line and each data point. The goal of regression is to find the equation for the line that minimizes the distances between the line and each data point. And so in the equation, you'll notice y hat that I have here, right? So y equals bx plus a is y hat equals bx plus a. Y hat is that is the value of y predicted by the regression equation or the regression line for each value of x. So the distance between the actual data point, y, and the predicted point on the line, y hat, is defined as y minus y hat. You might think of y as like a mean, an average, right? In other words, y minus y hat is the distance each data point is from the regression line. It's called error of prediction. The regression procedure produces a line that minimizes total squared error of prediction, the least squared error solution. All right. All right. In the regression line equation, y hat equals bx plus a, the slope of the line, b, can be calculated. All right. The slope, how much there is rise, run, right? Rise, run. The value of the constant a is determined by a equals my minus bmx. And we'll look at this equation in a moment here and how to calculate all that. All right. So we've already one great thing about regression is it kind of builds upon correlation. So it's very similar. Here we have data for X and Y and the mean for each of these data. So when you see this MX, it means the mean for your X values. The mean for this is 4, and for your Y values, it's 7. And you take these and you subtract them from from your X and Y values. All right. So far, so good. We've done this before. The values have been used to compute the deviation scores for each X and Y value. Remember, these are deviations, how far away from the mean they are. The final 3 columns show the squared deviations of X and Y and the products of the deviation scores. So here we squared all of these values, these deviations, right? And then we sum them up, sum of squares. So once we sum them up, we find these values. But we also have to calculate for their products. We have to multiply, right? All right. All right. So far, so good. We've seen this before. Oh, and by the way, when I say, I should have mentioned in correlation, but hopefully you've made it this far in the video. But when we're doing products, we're not multiplying these two scores. We're multiplying the deviation scores, okay? All right. As you can see, the formula does not have you square them, right? We're actually multiplying the initial deviation scores, not the squared deviation scores. So if you were looking here and saying 1 times 9 does not equals 3, well, that's because we're multiplying it from over here, okay? All right, so next. For these data, so far we've found that the mean for Y is 4, the mean for X is 4, and the mean for Y is 7, and the sum of squares was 28, and the sum of products was 56. So now we need to find the values for B and A in the regression equation. So here's this regression equation, and to do so, we can plug in what we have found so far. We have the sum of products, and we have the squared sum score, the squared sum scores, right? 56 and 28, and we find that answer is 2. Okay, so B equals 2, rise, run. And you can think of it as 2 over 1, right? So if we rise 1 and move over 2, we would find that value would be right about there. Okay. All right. And then we would plug it into the next step in our formula. So to calculate for A, it equals the mean of Y subtracted by B times the mean of X and we plug in the values we have so far. So the mean of our y values was 7, and we subtract by that, well, we subtract by the product of 2 and 4, 2 being what we calculated for b, and 4 being the mean of x. And we come to -1. So y hat equals 2x minus 1. All right. All right, and I will also put in this video. We have quite a few videos for for this chapter, just for some extra practice. It's a little different from comparing means like we did for t-tests and ANOVAs. So the more videos, the better, I sort of figured. So you can see again, step by step, how do you calculate for these equations? And I'll include that in this week's module. All right, error in regression. How do we calculate? So we have a scatter plot showing data points in A that perfectly fit the regression line defined by the equation y hat equals x plus 4. Note that the correlation is r equals 1, perfect relationship. B, we have a scatter plot for another set of data with a regression equation of y hat equals x plus 4, but notice there is error between the actual data points and the predicted y values on the regression line. So we don't have a perfect correlation here, but we have the same formula. What do we do now? All right, so the regression equation allows you to make a prediction, but it does not provide any information about the accuracy of those predictions. So keep that in mind. To get accuracy, it depends on how well the points on the line correspond to the actual data. Precision of the estimate is measured by what we call the standard error of estimate. It gives a measure of the standard difference between the predicted y values on the regression line and the actual y values. So it looks very much like standard deviation, okay? And you can see here how we calculate for standard error of estimate. And we've already calculated these values, the y and y hat. So it would be very easy for us to make this calculation with the data we've already evaluated. All right, so then find the sum of squared deviations, sum of squares, called SS residual. Residual is based on the remaining distance between the actual y-scores from the data and the predicted values y from the regression line. Then the sum of squares value is divided by its degrees of freedom to obtain a measure of variance. Degrees of freedom for a standard error of estimate is n minus 2. So in the denominator, it would have 2. All right, so let's look at what we have here. The data have the regression equation y hat equals 2x minus 1 and degrees of freedom n minus 2 equals 6. We had 8 scores. The standard error of estimate then is like so, and you can see how they've calculated for the variance here to arrive at the SS residual and also for the predicted y values or the residual y minus y hat. All right. All right. And we end up with 2.708. And of course, in order to arrive at these values, y hat, you would have to take this formula and calculate, right? We have y hat equals 2x minus 1. So if we say 2 times 5 is 10 minus 1, we would arrive at 9. Yes? And going across, you'll find that's how all of these are calculated. And so now we know what the values for y hat are. So we plug it into this formula, y hat, and we minus we minus that from the y scores. So 10 minus 9 equals 1. All right. And then we take that, the next step, and square all of these scores, and we end up with squared residual. So hence, this is how we arrived at 0 and 44. All right, and so I provided yet another video for standard error estimate. And yes, you guessed it, I will place it in the module as well. The standard error of estimate is directly related to the magnitude of the correlation between X and Y. So if you recall, if we're calculating for Pearson's, we know that it can go from 0 to 1, depending on how strong the relationship is. The standard error of the estimate can decrease to 0. So as the data points are clustered close to the line, the standard error of estimate is small, meaning you have less error. So note that when R equals 1, the prediction is perfect and there's no residuals. Predicted variability in Y-scores is calculating using SS regression. And here's the formula. Unpredicted variability in Y-scores, we can see the formula here. And then hence we can see the calculations or how to calculate it using these formulas. Standard error of estimate is based on R. So for example, if R equals 0.8, then R squared is 0.64, which when we turn that into a percentage, we see that 64% of the variability for the Y scores is predicted by the relationship with X, and the remaining 36% is the unpredicted portion. And you can see visually how all of the relationships exist here, right? All right, partitioning of SS or sum of squares and degrees of freedom for analysis of regression significance testing. So the variability for the original Y scores, both sum of scores and degrees of freedom, is partitioned into two components, right? So before we were trying to calculate what is the formula for that regression line, so we can make predictions based on data we might have in the future. Now we want to know, is the results we get when we do regression significant? All right, so the variability for the original Y scores is partitioned into two components, like I was saying. The variability that is explained by the regression equation that we calculated for, and the residual variability. All right, so analysis of regression. So it uses an F ratio of two mean squared values. Each mean squared value is a sum of squares divided by its degree of freedom. And so here, HO is the slope of the regression line is 0. All right, so it's 0 when it's a null hypothesis is true. And you can see the formulas to calculate for those partitions, the mean squares regression, as well as mean squares residual, and then the F statistic. So how do we do that? The F ratio for the analysis of regression has degrees of freedom of 6, right? And the way we do this is for SS regression, the degrees of freedom is the number of groups minus 1. So we have 2 groups. So if you subtract 1 for that, we're left with 1. For SS residual, degrees of freedom is the number of scores minus 2. Now we're only talking about the number of scores for both groups because we're assuming that both groups have the same number of people, or it is the same number of people because it's the same person being evaluated on two different variables, right? They are being evaluated maybe on their height and their weight. So we only have 8 people and we subtract 2 from that. So SS residual is 6. Our critical or our alpha level we've determined at 0.05, and we look up in the F statistic table or the F distribution table for the critical value using these degrees of freedom and find that the critical value is 5.99. By the way, the SS residual is considered the denominator in the distribution table. All right, for sum of squares for the y-scores, these are partitioned into two components, predicted and unpredicted variability. So SS regression, if you recall, this formula we briefly mentioned a moment ago, these are how you calculate it. Oh, all right, so as you can see, we've done the same steps here again. We've subtracted the scores by their means. For these columns, we've squared them. For this column, we've calculated the product of the deviation scores. And so we have sum of squares for X and sum of squares for Y, as well as the products. Now, we can plug that into these formulas, right? So we have R equals 56 over the square root of 28 times 156 right here. And we obtain that from the sum of squares here, that 2856. And on top is the products of 56. So when you divide, you have 0.84. All right, then we can calculate using these formulas. So SS regression, which is the predicted variability in the y-scores, you have R squared, right? And we had the R squared was 0.847, and then we multiply that by sum of squares for y, and we come to 112.01. Then you calculate for residual. It's basically the same formula, only in this first step, you're subtracting R squared from 1. And that would be what's left over. And it is 43.99. And by the way, if you take that first calculation and you add 43 the other calculation to it, you'll find that the total equals 156, which was sum of squares for y. Okay, and then we can take the answers we've arrived at here and calculate for mean squares regression, residual, and the F statistic, just like we did in the ANOVA, right? Right, and I have a snapshot of that right here in the outcomes. Simply plug in those values. And so the final outcome is 15.28. The F ratio is in the critical region, so we can reject the null hypothesis and conclude that the regression equation does account for a significant portion of the variance for the y-scores. All right, let's do a learning check. Let's say you have a linear regression that has V equals 3 and A equals 4. What's the predicted value for Y? Remember, that's Y hat for a score of 7. Ooh, that's an interesting one. If you take that equation and you plug that in, the numbers provided, if you have to remember what the equation was, you should be able to find the result. And it would be 25. All right. A little more practice. Is it true that it's possible for the regression equation to place none of the actual data points on the regression line? That's a good question. All right. Is it true that R equals 0.58 if R equals 0.58, that the linear regression equation predicts about 1/3 of the variance in the y-scores? That's a good question too. All right, the first one is true. The line estimates where points should be, but there are almost always prediction errors, right? You never have a perfect relationship. You never have all of the scores falling directly on the line. All right, there's always some error. Also, the other one is true. Remember, we look at the percentage of variance by squaring R, and it would indeed come to about 1/3. All right, the last slides just show what an output for correlation would look like, and I believe the other one is for regression. So if I am comparing variables 1 and 2 with each other, you'll see the Pearson's correlation outcomes for them. Remember, a perfect score is 1 and a perfect and no relationship is 0. So when I compare variable 1 to itself, you'll see it ends up with 1, which makes sense because if I'm comparing a variable to itself, it would have a perfect correlation. When I am comparing it to the second variable, I get 0.875. Well, that's pretty close to a 1. And to know if that is significant, I would have to look at the significance test, which you will see when you do SPSS. And if you have a significant relationship, you'll see SIG right there. That means it's giving you the p-value. In this case, it's 0.052. And it's telling you how many people were in this data set, and there were 5. Also here you can see variable 2 being compared to the variables, and you see when it's compared to itself, you have 1, right? Because it's being compared to itself here, but on this side, it's being compared to 1. This here is an exact mirror of what's down here, right? So variable 2 compared to variable 1 here is 0.875. Variable 1 compared to variable 2 is also 0.875, same thing. All right, here is the output or something you would see if you do a regression equation. You can see that it's giving you the model summary. It will have a box that's called ANOVA, where it gives you the F-test to tell you if you have a significant measure or not. And you can see it gives you sum of squares for regression and residual, as well as the degrees of freedom, the mean square, and the F-test. Everything that we learned how to calculate, right? And then the coefficients give you a t-test. So if they're related to each other, each individual itself is also being compared down here, right? F-test is done because a lot of times linear regression is used to compare more than one variable. So it sort of takes them all together and tells you if there's a relationship between them. The coefficients will tell you if there's a relationship between uh, each of these variables and its dependent variable. Up here, this is where you find effect size for regression, and it would be right here under R squared. So you can say that 71% or almost 72% of the variance is accounted for by the dependent variable. All right. All right, that's what we've got for chapter 14. We've got one more chapter to go. I look forward to seeing you in one more week. See you later.